Dear students, continuing with the photochemistry of aromatic compounds, in this lecture we will discuss about photo-substitution reactions of arenes. The photo-substitution reactions in case of aromatic compounds, they take place through heterolytic fragmentation of the either aromatic ring or the substituent present on the aromatic ring. And these photo-substitution reactions, they can take place in two manners. Likewise, we have defined them as either type 1 or type 2 photo-substitution reactions. In the first category, the photo-substitution reactions of those types are included where the orientation rules, they are different from what rules we follow in the ground state. Ground state means the reactions which take place by thermal reactions, they have different rules, orientation rules as compared to photochemical reactions. So this is the type 1 photo-substitution reaction. And second category of photo-substitution reaction is type 2 substitution reactions, where the orientation rules, they are same as followed in the ground state. But here only difference from the thermal reactions is that here the rate of the reaction gets increased due to absorption of light through photochemical reactions. And in addition to these two types, there are some substitution reactions which take place photochemically by radical mechanism. So we will discuss all these three types of photo-substitution reactions which take place. So first is type 1 photo-substitution reaction. In this category of photo-substitution reactions, either these substitution reactions, they can take place by the attack of a nucleophilic species or by some electrophilic species. If the nucleophilic species is involved, we say photonucleophilic substitution reactions. And if an electrophile is the attacking species, then we call those type 1 photo-substitution reactions as photoelectrophilic substitution. So first is photonucleophilic substitution reactions. And here if we take say the case of nitro group, which is an electron withdrawing group, and as far as this electron withdrawing group is concerned, nitro group in the ground state, it acts as a orthoparatrectic group. For example, you can see this reaction where when we react potassium amide in presence of liquid ammonia with nitrobenzene, then amination of this nitrobenzene will take place at ortho and para position, and para product is formed as the major product in this case, and we call these thermal reactions as ground state reactions. Whereas when the same reaction is done through excited state, that is through photochemical nucleophilic substitution, then this nitro group becomes meta-attractive. For example, we take the case of 3,4-dimethoxynitrobenzene. Now, when this reaction is done photochemically in presence of potassium amide as the base and an alkali as the nucleophile, then the substitution of this nucleophile will take place at the meta position of the aromatic ring. So the photonucleophilic substitution of this compound under photochemical conditions will be a meta-directing product will be formed. But if the reaction is conducted under thermal conditions, in presence of same reagent, potassium amide and sodium hydroxide or potassium hydroxide as a base, then the substitution of the methoxy group will take place at the para position. So as you know, this is a ground state reaction and this is an excited state reaction. So in photochemical nucleophilic substitution reaction, nitro group is a meta-directing group, whereas in a nucleophilic aromatic substitution under thermal conditions, that is in the ground state, it will act as a para-directing group. So this is the difference between ground state reactions and excited state reactions. Similarly, if we are having this 3-methoxy nitrobenzene, we react in the excited state in presence of methylamine as the solvent, then substitution of this methoxy group by this nucleophile will take place at the meta position. So here also, because the reaction is taking place in the excited state, the nitro group becomes the meta directing. Then other electron withdrawing groups like cyano groups, they also behave in similar manner as we have seen in case of nitro groups. And if we replace this benzene by naphthalene, then also we will get the same type of reactions, that in the ground state we will have orthopara-directing nitro group, and in the excited state we will have meta-directing nitro. Then some more examples of photochemical nucleophilic substitution reaction. When this 1,2,4,5 tetracyanobenzene is reacted with 1,1-dimethylalene in the presence of diphenyl, then this type of photo-substituted nucleophilic product is formed. And in this reaction, the role of diphenyl is very important as far as conversion of this tetracyanobenzene into this photo-substituted product is concerned. The mechanism of this reaction is that the diphenyl basically act as a co-donor to drive the reaction in the forward direction. So what happens is, in the first step, the tricyanobenzene, when this is irradiated, then it goes into the first excited state, and this excited tricyanobenzene then reacts with diphenyl, which act as co-donor, and on reaction with diphenyl, the tetracyanobenzene is converted into an radical anion, whereas diphenyl is converted into a radical cation. And then this diphenyl radical cation reacts with the other substrate, that is dimethylalene, and the dimethylalene becomes a radical cation, and this diphenyl comes back to its original ground state position. This diphenyl dimethylalene radical cation then reacts with the solvent, that is methanol, and with the elimination of a proton, this is converted into this type of radical. Then this radical reacts with the tetracyanobenzene radical anion formed in the first step, like this. These two, they interact, and this CH2 negative radical will attack at this position, and we will get this type of radical. And with the elimination of cyanide negative, this will be converted into our photo substituted product. So this is how the photochemical nucleophilic substitution in case of tetracyanobenzenes and 1,1-dimethyl allene gives us these types of photo-substituted products. Then another type of substitution, as I have already told you, is photoelectrophilic substitution. That is when arenes they are having an electron releasing group attached to them, say in case of toluene or anisole, when here we are having methyl group which is electron releasing in nature, or methoxy group which is also an electron releasing group. They are photoradiated in presence of trifluoro acetic acid, deuterated acetic acid. Then deuterium will be acting as an electrophile, and it will add to this meta position of the aromatic ring. So when the electron releasing groups are there, then this electrophile will act as a act at a meta position. That means these electron releasing groups, they are meta directing in photoelectrophilic substitution reactions. Whereas if we use the electron withdrawing group like nitro group, then these photoelectrophilic substitution reactions, they will be para or ortho substituted products, they will be formed. And these orientation effects, they are different from the orientation effects which are observed in case of ground state reactions. So in all these photochemical reactions, the ground state products, they are different as compared to these photo product or excited state products. Now, why there is a difference of formation of products in case of excited state and ground state? So if we take the example of photonucleophilic substitution reactions or photoelectrophilic substitution reactions, you have seen in the previous slides that in case of photonucleophilic substitution reactions, if there is a nitro group, the product formed is at the meta position. That means nitro is acting as a meta directing group. Similarly, in case of photoelectrophilic substitution reactions also, if we are having electron releasing group, they are acting as meta directing groups. The basic reason for this type of behavior in the excited state is dependent on the charge density at the point of attack. So, as we know that in case of photonucleophilic substitution reaction, the attacking species is a nucleophile, whereas in photoelectrophilic substitution reactions, the attacking species is an electrophile. So that means nucleophile will attack at that position where there is more of positive charge, whereas electrophile will attack at that position where there is more of negative charge or electron density is more. Here nucleophile will attack where electron density is less. So if we observe the first excited state in these cases, for example in case of nitro, when the ground state is radiated and it changes into the first excited state, then this type of intermediate will be formed with the movement of the electron density like this. This carbon-carbon double bond, that will form a carbon-carbon bond at these two places, and this bond will shift to this place. This oxygen, which is more electronegative, will require the negative charge, and we will have the lesser electron density, that is positive charge, will be created at this meta position with respect to the nitro group. And in case of photonucleophilic substitution reactions, as I have told you, the attacking species is a nucleophile. So nucleophile will attack at a point where the electron density is less. So that is why this will attack at the meta position, and ultimately we will get a meta product. And That is why the photonucleophilic substitution reactions, the nitro group is meta attracting. Now similarly in case of photoelectrophilic substitution reactions, because of the presence of lone pair of this oxygen, the electron density will move on irradiation like this, and here we will be having a negative charge. And because of this, the electrophile will attack at this position because this is having more electron density. And because of this, the electrolyzing groups in case of electrophilic photoelectrophilic substitution reactions, they also behave as meta attracting. So on the basis of the charge density or electron density at the point of attack, we can explain the formation of different types of products in photo substitution reactions. Then is type 2 substitution reactions. These are those reactions where the orientation rules which are followed, they are same as in the ground state. And here only difference is the nucleophile which we will use will always be a neutral nucleophile. So for example, when nitrobenzene is photoradiated in presence of ammonia as the solvent, then this will act as a para directing or ortho directing group. In this case, because here the nucleophile will be a neutral nucleophile, and rules of the orientation rules followed will be same as in the ground state. Then third category is radical substitution reactions, and here in other two types we have seen the heterolysis of the bond. Here homolysis of the bond will take place. Aryl haloarenes, they will undergo homolysis of this bond, ARX bond, and we will get aryl free radical and halogen free radical. And similarly, when chlorobenzene is photoirradiated, then in presence of the solvent, a solvent cage is formed between these two radicals which are formed. And this solvent cage ultimately leads to the formation of a pi complex between the aromatic ring and the halogen. And this halogen atom of pi complex is more selective than halogen free radical which is formed in the absence of a solvent cage. So we will get more selective type of reactions when pi complex is formed in radical photo radical substitution reactions. Now some of the examples of different types of photo substitution reactions. The most common example is in case of iodinated aromatic compounds when they are photoradiated with a particular wavelength. For example, in this case, when we radiate this with wavelength of 254 nanometers in presence of benzene, then they will be converted into phenylated aromatic compounds. So this phenyl group will be substituted at this position, H from here, H radical from here, and I radical from here. Hi will be eliminated, and we will get phenylated aromatic compounds in 90% yield from these reactions. Similarly, if this type of substituted iodo substituted phenol is photoradiated at this wavelength in presence of benzene, then all the three iodide atoms present at these positions, they will be photosubstituted by 3 benzene rings, and product is formed in 75% heat. Some more examples here. All these examples, they belong to intramolecular photosubstitution reactions. For example, if we are having these two iodophenyl naphthalenes, and H from here and I radical from here. So this will be photo substituted at this position, and we will form a carbon-carbon bond with the elimination of iodide radical from here and H radical from here, and we will get fluoranthene in 22% yield through photo substitution reaction. Similarly, this type of cis iodo derivative of benzene, when this is photoradiated, this undergoes intramolecular substitution reactions. So I radical from here and H radical from here, they will form a carbon-carbon bond, and phenanthrene will be photosynthesized from this type of photosubstitution reaction. Similarly, carbon-carbon triple bonded iodides, that means iodoacetylenes, they can also undergo coupling reaction with the benzene, which is used as solvent uh, in presence of photoradiation through intramolecular substitution reactions, and we will get diphenyl acetylenes as the product. Then photoradiation of metal dianions with aryl bromides or aryl iodides in liquid ammonia, they give phenyl acetic acids, isomeric phenyl acetic acids as the product. So basically what happens is aryl free radical and halogen free radical, they are formed. Similarly, either this will break from here or it will break from here to give us these two isomers, and M free radical and X free radical, they will form MX, and aryl free radical will get joined to this place, and similarly we will get the other isomer and arylation will take place at this place. H from here will be eliminated, and H radical will combine with X. HX will be formed, which will remove this metal ion present at this place, and this will be converted into an phenyl acetic acid, and arylation will take place at this position. Similarly, the natural product azulene can also undergo arylation to give us one aryl azulene in presence of aryl iodide when this is photoradiated. So these are the references which have been used for preparing this reaction, this lecture. Thank you very much.